Okay, so is it okay for my slides?
Yes, it is. Okay, so I'm going to introduce you, and we can start.
Mm-hmm.
Okay, so it's a pleasure to announce the first speaker of the session, Emmanuel Henry. He's
Yes.
going to he's going to talk about a tire-based typed programming language characterizing feasible functionals.
Yes, thank you. So to do a quick summary of our result, what we do is we have defined a characterization of type 2 polynomial time, so feasible functions, with a class that we call ST for safe terminating. And at the first level, ST1, so if we only apply it to numbers, natural, it characterizes polytime function of type 1, so functions from natural to natural. And at the second order, it characterizes functionals computable in polynomial time of type 2, with some with a few other constraints. The mechanism through which we work is that we've defined a programming language that uses oracles. So the oracles are the type 1 inputs for our language. And it's an imperative language with whiles, with you can make a query on the oracle, and you can do assignation, everything. So for an example, here is a really short program that decides whether there's an n smaller than the input x for which the oracle gets is 0. You can see that there are some blue and red numbers. Those are tiers. So the tiers allow us to stratify variables and expressions. And in this example, there are only 2 tiers, but in our result, we have k tiers. So constant numbers that can be as big as you want. And there's a non-interference constraint, which says data cannot go up in the tiers. It can only go from tier, let's say 1 to tier 0, but not the other way around. And so our result is both sound in that all BFF functions are in the class that we define, and complete, which means that for that if a function is computable in polynomial time, there is an algorithm that that is typable. So it's not extensionally complete, just intentionally complete. There exists an algorithm that we will be able to type, but there will also exist algorithms that we won't be able to type. And one last thing is that the type inference is decidable in polynomial time. Okay.
Thank you very much, Emmanuel, for the presentation. So I would like, so we have already a question from Slack, but before asking this one, and maybe I'll have another one as well. Is there anyone in the audience that would like to pose a question or discuss something about this? Okay, so let's move to the question that we have in Slack. Emmanuel, can you see the question in the chat?
Yes.
So
yes, the question was about termination technique. So I didn't say it, but our result relies on termination. We don't prove that the program terminates, but we prove that if it terminates, it's in polynomial time. And we say that it's possible to add some termination results to characterize exactly polytime function. So we have already thought about using size change principle, but this is a decidable technique, so it's not a complete. It's not complete, and the question was more about completeness. And we think that using some techniques that use well-founded iteration, well-foundedness, probably would yield, could yield a result on polynomial time, and with the same how to say. Well, it would be possible to capture polynomial time without this termination assumption.
Okay. And well, I have a question for you. I mean, I saw the video and I liked the video a lot. It's really nice. And there in the future work, you put two things there that I was really puzzled. The first one was this, how to get rid of the lambda terms. So could you talk a little bit more about that? Or what do you mean by that? I mean,
that's, I didn't say that, but in the second result, it's lambda of ST equal BFF because we need a lambda closure. If we don't have this lambda closure, well, the result we use from Capron and Steinberg says that we are strictly their class, which in fact we characterize, is strictly included in BFF. In fact, what's missing is that it's possible in BFF to compose an oracle with itself, while the constraints that Bruce Capron and Florian Steinberg put constraints that it doesn't really allow any every composition. So the composition is instead in this lambda closure instead of in our language. And we have ideas to put this lambda closure, to remove this lambda closure, but to have some latitude in the way we use oracles to be able to compose inside the language.
Okay, nice. And the other thing is that you also mentioned other extensions to capture more false negatives. Which ones? I mean, could you tell us a little bit about that? I mean, what are the other extensions you're thinking about?
Oh, I don't know. Not sure what Romain was thinking about when saying that, or what we were thinking about. No, I don't have an answer. Maybe Romain can input something.
Romain has answered in writing.
No, I think that Romain answered the first question, right?
Yes,
I mean,
it's for the other question. Yeah.
Yeah. Okay. Combination with other techniques in program analysis, shape analysis. Oh, interesting.
Okay. Yes, indeed, we are working on things like that at the moment.
Yeah, nice. I mean, yeah, this future work that you put there seems to be really challenging, right? And yeah, I like the session a lot. Okay, Manuel, so we have 1 minute. I mean, do you want to say anything else or?
Well, on my side, everything's okay. And
okay.
I'm happy. Well, the video was quite nice. It was Romain who did the full video. I'm only acting as Romain here because it seems his microphone is broken.
Okay, well, this is a teamwork, right? I mean,
yeah.
Nice. Okay, Roman. So thank you very, Emmanuel. Thank you very, very much for the talk and
thank you.
For the answering my questions. And so so this should be really dynamic, right? So we should move on. So let's move to Pierre now. Pierre, could you share your screen?
Yes. Okay. So just 1 second. Up, put that in full screen. For some reason, I cannot put that in full screen, but I will share my screen anyway.
Okay.
So here, do you see?
Yes, yes.
Okay. And how is it displayed? Sorry. Well, anyway, I will just change.
We see your whole screen with the menu, fichier, and column of vignette. Oh, sorry, the screen has just disappeared.
Yeah. Sorry. So, okay, I'm really sorry about that. Yes, now it should work. Sorry, I'm really sorry. Share screen, and this should be there. Yeah. Okay. So.
Okay. So next, so the next talk is going to be. So Pierre is going to talk about consuming and persistent types for classical logic, and the work is with Dale Kessner. Go ahead.
Okay, thanks. So yes, we captured exact measures of evaluation in the non-dynamic calculus. So just a small reminder, the non-dynamic calculus is a computational interpretation of classical logic. So it allows expressing control operators and do backtracking, etc. This is actually, it corresponds actually to a form of focused classical natural deduction with a new kind of reduction, which is called mu reduction. So for that, we use intersection types, which were used to characterize normalization properties initially. And by exact measures, I mean both the evaluation length to the normal form, the number of steps which are needed, and the size of this normal form. So actually, non-idempotent types were used to obtain exact measures in the lambda calculus, so intuitively in pure functional programming. So the question was, what can we do when we have control operators in the lambda calculus? So eventually, we obtained a type system, which allowed us to capture, with annotated judgments, which allowed us to capture exact measures of evaluation. We have the 3 letters L, M, and F in colors which correspond to the number of beta steps, mu steps, and the size of the normal form. If you have read the paper, actually, not all judgments are able to characterize that, but only a subclass which are called exact judgments. And we did that for 3 evaluation strategies, which are associated to 3 different notions of normalization. That is a normalization, weak normalization, and strong normalization. So a reminder for the main ingredients. The idea was to distinguish between persistent elements in a term, the one which remains in the normal form, the consuming ones, which are destroyed when we reduce the term. So hence the title of our talk. And for that, we use an explicit persistent, an explicit constructor for persistent things, which is a persistent arrow. But the problem was that because of duplication, it cannot be formally defined in the lambda calculus. So the solution was indeed to use non-idempotent types because it allows creating duplicates of terms before they are actually duplicated and make the notion formal on the type level. And last, we had to deal with control operators. So something that I did not discuss much during my presentation, but we needed to activate persistent arrows into consuming ones. I have a really small extra slide for that just after that. And we also had to capture the arities of functions, which is not necessary in the lambda calculus, in order to have decreasing measures which capture exact values. Thank you.
Thank you very much, Pierre. Yeah, so this presentation was really, really cool. I mean, I like the way that you keep putting things on the screen. It worked quite well for me, at least. I could understand most of the video. It was a great video. So we already had some questions in the Slack, and you answered them. So. Yeah. Yeah, so the first one I thought really intriguing because, you know, when normally when we talk about, you know, lambda calculus and let's say abstract machines. We never think about, you know, real life programming languages or how to implement these things, right? So both questions are more or less related to implementation somehow. And so do you like to talk a little bit about them? Although
yes.
They are
so the first question, I don't have it under my eyes, but it was about what could we do this for a real programming language like C++, I think, or Java. So I was not sure that the question, it was not a mistake, but intersection types or union types are really have a theoretical use. They are undecidable because usually they are undecidable because usually they capture normalization properties which are undecidable. So it was more about seeing what model can capture. And here we prove that we could actually capture exact measures of erosion. So it was very theoretical. So for the second question, it was, is it possible to, do you think that we may formalize that easily in Coq? And the answer is yes. Why? Because when you want to define non-important intersection types, the difficulty, as I wrote it, is to have to find your rules so that everything works fine. In the presentation, you may remember that you have only three typing rules, so it's really syntax directed. But once you have your system, all what you need to prove will be proved by structural induction on terms or on proofs. You don't need reducibility arguments. You don't need Gensen-like arguments of termination. So it should, I guess, it should be easy comparatively to other things.
Yeah, that's my feeling as well. So there's a question from Jacob. So I'm opening now questions from the audience. So Jacob, do you want to open your microphone and ask the question, or you prefer me to read? Or
yeah, sure. Hi Pierre, nice talk. Yeah, I was just wondering if you ever thought of relating such properties like the ones you showed here with the classical calculus, relating them to sort of corresponding properties for the image of CPS transforms. That means like studying how these properties relate to corresponding properties on the embeddings into intuitionistic logic of the programs.
So yeah, it's a good question. My feeling is that on one side, you have a system which captures exact measures in the lambda calculus. In another, on another side, you have a system giving you exact measures in lambda calculus. So if you study CPS translation, actually, the difference between the exact measures in the lambda calculus and the lambda calculus will just give you the number of it will give you, for instance, if you have a mu step, it will tell you how many steps it will correspond in the lambda calculus. I'm not sure I'm making myself clear, but
sure. I was just wondering, for example, if because it gives one the opportunity to ask questions precisely like, for example, if there might be a blow up under CPS transformation once you eliminate the control, right?
Yes. This is
so it's sort of like asking how much the control operators might buy you if you go the other way.
I guess the system could tell you that, but I'm not familiar enough with CPS translation to know it. The question is, would our typing rules make the study the study of possible blow up easier? And I'm not familiar enough with the topic to answer to give you a clear answer.
Okay, all right, something to think about maybe.
Yeah,
thanks.
Thank you very much, Pierre. Great talk. And I have some questions, but I think we're not going to have time for them. But for you and Delia, I can ask afterwards. So it's about the paper. So I'll do it via email. Okay. So thank you again, Pierre. And
I will unshare the screen. Yes. Okay.
Yeah. So for the other paper, I'm not sure. Maybe Michaela can tell us, but I don't see Artur there or any of the nobody there, right? For the D.
No, me neither.
Yeah, no one, right? So let's move to the D. So
yeah, and in the end, we can ask again if someone is there.
Yes, sure. Let's do it.
Just written a very quick email to the authors that they should join the session now, but I think the best is to go to Rohit Chaudhary.
Yeah, let's go. Let's go to Rohit. So Rohit, are you there?
Yes.
Yeah.
So I'm about to share the screen. Hopefully it will work. Does it work? Can you see?
Yes. So
okay.
Next talk is going to be by Rohit Chaudhary, and it's going to be on deciding differential privacy for programs with finite inputs and outputs.
Hi. The problem that we're considering in this paper was verification of differential privacy. So the scenario is that you have databases with private information, and you want to perform some queries on these databases, but you want to have some useful results, but also you don't want to compromise the privacy of individuals in the databases. So differential privacy framework is basically a framework in which you try to accomplish both functionality and privacy. And the key idea is that when you actually query a database, the database doesn't give you back the exact answer. It gives you an answer which is slightly perturbed. So there is so think of it as there's a program that takes the output of the query and gives you a slightly perturbed answer. And essentially, this program is a randomized algorithm. So with some probability, it gives you some answer. Some other probability, it gives you some other answer. And the differential privacy definition is complicated. I won't go into it in detail, but essentially, it's something like this: that if there are two databases which are almost equivalent, then the probability that the first one gives, that the two give the same answer, must be related by some equation, and that equation looks something like this, which is probability that the output of the differential privacy mechanism on the first query is less than equal to e to the epsilon probability of the second mechanism giving the answer on the second on the query on a similar database. And so basically differential privacy verifying boils down to checking equations of these forms. And you can see here already that you have an exponentiation function e to the epsilon, and also there is more complication in the verification, in the sense that this mechanism itself changes with epsilon. So the probability of obtaining an output can vary with epsilon. So what we have done in this paper is basically to show that if you want to check differential privacy of very simple randomized programs, then the problem easily turns out to be undecidable. That's not a surprise. Everything interesting turns out to be undecidable. But what more interestingly, we showed that that the problem of checking differential privacy is decidable for an interesting class of programs. Our decision procedure can check differential privacy as well as generate counterexamples. We also check differential privacies for all permissible values of this parameter epsilon that I showed you before. We are the first such result that encompassed sampling for both integer and real valued distributions. So basically, the randomization, the random sampling can sample integer and real value distributions, and basically the main idea in the paper is to reduce it to a question of satisfaction of a theory of fields with exponentiation. And since we don't know what this whether this theory is decidable or not, we are careful to map it into a fragment which is known to be decidable. And we actually implemented this decision procedure and evaluated on some small private and non-private examples. And one sort of advantage of a tool is that it can not only generate counterexamples, but also it was the first tool that could check for epsilon delta differential privacy. So if you go back here, there are two parameters, epsilon and delta. Most techniques for generating counterexamples or verifying differential privacy only work with epsilon. In our case, we could work with both epsilon and delta. So that's what.
Okay, thank you so much. Interesting. So is there any questions from the audience before I pass to the Slack? Okay, so in this Slack, there is this question about, actually it's about if the results that you have is escalate for bigger queries, right? I mean, so they're saying that you run for 3 queries from domain from -1 to 1, and David Janssen said that. Huh?
Yeah.
Sorry.
Depend blue.
Yeah, depend you. Sorry,
yeah.
David. Depend you asked if you could do that for 10 queries, and what would how this would affect the results or the complexity of the formulas that you have to validate.
So, so the formulas will explode as we increase the number of queries. So Depeng also asked there whether we think it's possible that differential privacy is violated only in larger settings, say 10 queries. And of course, the answer is yes, it's possible. But there is some work by the group of Daniel Kiefer and Danfeng Zheng and others, which showed that for many classes of or many interesting differential privacy mechanisms, they were able to show that they were able to find counterexamples with a small number of queries, say 4 or 5. So in theory, for sure, it's possible that 10 queries can explode the algorithm, or the performance can degrade the performance, and I will just leave it as that.
Okay, well, thank you very much. So is there any other question? So thank you, Rohit, for the very nice talk. So so now I see that Artur came, just joined the session. So maybe Artur, do you want to talk now? Or you want to share your screen?
Wait, I have to unshare.
I still need a few minutes to set up, if that's okay.
Okay, yeah, sure.
Would you prefer to have another paper discussed first before, or do you want, or shall we?
I think that would be better, actually.
Okay, Artur, so we're going to wait a little bit. So Etienne, so are you ready? So can we start sharing your screen? Yes, so, okay, so we can, I'm going to wait 1 more minute, then we can start. But I can already introduce Etienne Miquet, and so he's going to present a work with Hugo Berlin, and the work is on a calculus for expandable stores, continuation and environment passing style transformations, and yeah, so you can start.
Okay, so you can hear me?
Yes, Etienne. Yes.
Right. So thanks for the.
Etienne, can we also see you?
Yes.
Excuse me.
Wait. Is that okay? Right. So indeed the paper that we wrote with Hugo Herbelin is about actually continuation and environment passing style translations. That's a long name to say that these are some kind of CPS translation that are, I guess, most well known, to which we want to add something to take into account a global environment. So you can think of a compilation process during which you want to have an environment that you pass also with the continuation. And we want to type the whole thing, and that's the main difficulty. And to that end, we developed a new calculus, which is the calculus with expandable stars. We named the paper after. And in this paper, we have something to deal, a data type to deal with the type stars, and we have a mechanism of explicit coercions that we use to witness the star extension, and in particular the way we type the star extensions. And if we want to see just one, oh, let me find this, just to have a glimpse at how the translation is working. So when maybe we can start here. When we have a CPS, a usual CPS translation, what we do is just we have some negations everywhere to say we are passing a continuation and the return type is bottom. But in this setting, it's much more tricky in the sense that we need to take into account, of course, the continuations, that the part which is returning to bottom here, but we also need to take an environment here whose type is related to the typing context in the original calculus. And we need to take into account that this star, this environment might be extending during the computation. That's why we have this subtyping relation. And then we have components to get a sound. And in the end, we are pretty happy with the result because we managed to define this kind of translation for both call by value, call by name, and call by need calculi. So the calculus we define is pretty generic in that regard. That's, I think, the summary of what we've done.
Yeah, it's a good summary. Thank you very much, very much. So is there any questions for from the audience first? Because there are some in Slack and I have mine as well. So no questions? So let me ask you first mine. So at the end of your talk on the video, you said, you know, some words about the translation that you have and the relationship with this with modalities. So I know that you're based on a crypt structure and everything. Could you tell us a little bit more about that?
Sure. So in the slide that I was showing, so if we go back to the of a usual CPS translation, that would be this one. We can see the negation as some kind of modality, and somehow what we did was to refine this modality in order to take into account here all these components. And so we have a way to present the translation using a box that looks ready, but we didn't do what it has property. So we could work whether it has anything in common with the usual property, for instance, for the negation that we have in CPS translation, and well, somehow if it is connected also with Kripke forcing, because it's more complex than Kripke forcing because of the continuation passing part of the negation that is in the end. So, and Kripke forcing could also be presented as a modality. So it's natural to wonder whether here we have something which still have some interesting property or not at all.
Interesting, nice. So now there's a question from Slack. do you see it there or?
Yes.
Yes, right. So, yeah. So,
so the
yeah,
question, as I understand it, is somehow to explain if our setting allows to draw the comparison between different evaluation strategy better than in the original calculi. And for that, I would say that in the one hand, there are many ways of presenting the calculi. So each way of presenting it with some, let's say, some big step rules or more close from an abstract machine or as a CPS translation as we did. Each way of presenting the calculi has some particularities and emphasize some specificities. And on the other hand, I would say that on our specific setting, it has the benefit of giving a uniform framework in which we can express all the translations and all the calculi. And what it really emphasizes, I think, it's the way the environment, the global environment is typed, and how the extensions of the environment are preserved or are made sound with respect to typing along the computations. So this is what's hard to do to get the translation, but this is what it shows, I think, best with respect to the original calculi, the original presentations of the calculi.
okay. Anyone else has questions? So thank you again, Etienne, for the nice talk in the video. So then maybe we can move on to the next speaker. So Arthur,
Yes, I'm here.
you're there. Okay. So can you share your screen?
Absolutely. Let me do this. Let's see if I can get this to work. These are my slides. Okay, so sorry for the hiccup before I start. I had some time zone confusion, but hopefully it should go smooth from now.
It's okay. So Arthur is going to talk to us about reconciling non-interference in gradual typing. It's all up to you, Arthur.
All right, cool. So I'll give you a quick overview of this work that we've done. As the title says, this work is about trying to reconcile non-interference as you find in languages for information flow control like GIF and FlowCamel with this novel idea of gradual typing that tries to combine the best of both dynamic typing and static typing. So what's the deal here? Well, in the gradual typing literature, people have converged on a set of soundness criteria for that gradual languages should ideally satisfy. One of these criteria, let me jump ahead a little bit, is this thing called the dynamic gradual guarantee. What is the idea? Well, you have some program that is perhaps dynamically typed, has no typing annotations. It gives you some results. Now, what happens if you add in some typing annotations to this program to try to make its behavior more robust? Well, the dynamic gradual guarantee says that this annotation cannot interact with program behavior in arbitrary ways. There's two things that can happen. Thing number one, the program returns the same result. Thing number two, the program results in an error in case the type contract imposed by the type annotation is violated. It cannot be the case that the program returns some completely different result, right? Now, what's interesting is what happens if the original dynamically typed program resulted in an error, perhaps because it tried to add a string to an int or something like this. Well, in this case, the annotated program should produce the same error. So this is the idea of the gradual guarantee. Now, when people started to study how gradually typed languages for information flow control fared with respect to this criterion, they realized that all of them, albeit sound from an information flow control standpoint, failed to satisfy this dynamic gradual guarantee. So Matthias Toro, Eric Tenter, and Ron Garcia looked at this situation and said, well, can we come up with a better language for information flow control based on this principled approach for gradual typing that we came up with called abstract gradual typing. And one of the advantages of this approach is that it provides the dynamic gradual guarantee by construction. When the authors tried to do this, they realized that they broke non-interference. They managed to restore non-interference by tweaking the language that they obtained by applying this methodology, which unfortunately resulted in a design that broke this dynamic gradual guarantee. And they asked themselves, well, is it the case that there's a fundamental tension between information flow control and gradual typing, or can we fix this situation? So this paper is about showing that actually these things are not incompatible. And I want to just give you a quick idea of what the problem is with previous approaches and how we managed to fix this. So in information flow control type systems, let me see if I can get to this, you have this these secrecy annotations that you attach to variables, right? Now in dynamically typed IFC, you have no static secrecy annotations. These things are all determined at runtime. The issue with previous designs was that if you add in a secrecy annotation, a static one, this thing ends up interfering with the, let's say, the dynamic secrecy associated with this value, which in turn ends up affecting these monitor checks that are used in information flow control to prevent information leakage. So what we realized is that, well, actually, you can satisfy all the requirements of information flow control and the dynamic gradual guarantee simply by changing the checks that are associated with these static annotations. Now, instead of classifying the value dynamically, changing the secrecy data that is associated with it, we're simply going to check that the ascribed secrecy value, the one that we gave statically, is compatible with the dynamic secrecy that was computed by our information flow control monitor. And if this is the case, we allow the program to proceed without changing this dynamic secrecy information associated with the value. So at the end of the day, what happens is that adding this annotation does not affect the execution of the program as expected, as imposed by the dynamic gradual guarantee. Unlike these previous approaches where, well, if you add in a type annotation, you end up affecting how your program executes in a way that breaks the dynamic gradual guarantee. And well, our approach is pretty general in the sense that you could adapt it to a variety of IFC languages that have been proposed in the literature. But in this paper, we introduce a particular incarnation of this approach called this GLIO language for gradual LIO that is based on this Haskell library for information flow control. And we simply show that, well, this thing can be endowed with a gradually typed type system that gives you both a dynamic gradual guarantee and non-interference. From a technical standpoint, one of the things that's interesting about this work is that to prove soundness for this language, we had to reason about higher order store, which can be tricky. And we solved this issue by taking a somewhat unorthodox approach by today's standards, which is to define these logical relations using domain theory, and more precisely, this framework of relational structures of ND bits, if you're familiar with that line of work. So this is a very high level of review of this work. I don't know how much of this makes sense in this short time. So if you have any questions, I'd be happy to take them.
Thank you, Arthur. So is there any questions from the audience? Because we didn't have any from the Slack. In your video at the end, you said that you should make some more study about information flow control, right? In which sense?
Well, there's this question of how do you design an IFC language that people can actually use, right? One concern that people had with statically typed IFC languages like GIF, for instance, or FlowCamel, is that these type systems sure manage to enforce information flow control, non-interference, but they are pretty complicated to use, right? In the dynamic setting, you alleviate the situation a little bit because you need fewer annotations for these programs to run, but you still need to attach secrecy information dynamically to these values. So in our language in particular, which follows this LIO approach of doing things, when you allocate a reference, which is this new construct here, you have to annotate it explicitly at runtime with a label value. And this is weird from the perspective of a normal programming language because, well, when you allocate an object on the heap, you don't need to impose this information, right? So what this work made us realize is that, oh yes, there's a, so why is this important? Well, because the dynamic gradual guarantee is about giving you, well, guarantees when you add in type annotations to some unannotated program, right? But really what you want to have in this case is a guarantee that applies also to adding in these dynamic annotations, because these are the things that are missing from normal programs that you find out there in the wild. And what we've been considering after, well, reconciling non-interference and gradual typing is maybe a language design where you don't need these intermediate label annotations here because they are somehow inferred by the context in which you run your program.
Okay.
Does that make sense? Yes. I see there's another question in the group chat.
So Naoki, would you like to ask the question or?
Yeah, I wrote a question in chat. So in your type system, only security labels are gradual. So is there any difficulty in making security types, ordinary types also gradual? So is that orthogonal issue or?
Yes, I understand the question. I believe there wouldn't be any difficulties. The reason we chose this design is that, well, in the gradual typing literature, there's one feature of the type system that people choose to focus on when trying to make it gradual, and they leave everything else static, right? So what's dynamically typed, in a sense, is up for grabs. Now, it would be possible to go further down, make the language more dynamic, right? By allowing you not only to say that the secrecy value, the secrecy level of a value is unknown statically, but also its type. So you would take something of type dynamic or question mark that could be maybe a reference or a function, etc. And the thing is that these type checks don't really interfere with information flow controls.
But one of my concerns is that in ordinary gradual types, they insert coercions, but the result of that coercion may leak some information.
Yeah, I don't think that coercions would induce a problem here because, and let me see if I can give an intuition for this. So you can think of values in this language as a tagged union, right? If you were to make it completely dynamically typed, it can be either a reference or a function or something. Now the question is, does this type tag leak some information in any way? The answer is...
but I'm sorry. So yeah, there are great
we
questions.
Could discuss offline.
We can discuss about this until tomorrow morning.
Yeah, we can take this on Slack maybe or
yeah, I would like to thank you, Artur, again, and Naoki for the question. Thank you very much. So maybe you can discuss this in Slack. I think it's all very interesting.
Yeah, sure.
So we should move then to the final, the last speaker of the session. And well, I would like to announce that after this session, there's going to be the eAtax award session. So I invite all of you to come and join. We can announce we can put the well, David can put the Zoom link in the chat afterwards. Okay, so it's going to be a nice ceremony just after this this nice very nice session we're having now. So the last speaker of the session is Takeshi Tsukada, and he is going to talk about computability of logical approaches to branching time property verification of programs. So it's up to you, Takeshi.
Yeah, thank you for the introduction. So this talk is about program verification, and in particular, so-called branching time property verification of programs. And so many approaches, many logical approaches has been proposed to solve this problem. Here, logical approaches means that reduction of the verification problem to some logical problem, such as the validity problem or satisfiability problem, and so on. And many logics has been used to this purpose, used for this purpose. For example, some extension of arithmetic by fixed point operators, or some generalization of constraint Hom clauses and second order arithmetic and other. Okay, so let me briefly explain the background of this talk. So the properties of programs can be classified into three: safety property, linear time temporal property, and branching time property. And the safety property is one of the most important class in practice and has been very, very extensively studied. And its hardness is very well known. It is pi 01 complete. And recently, approach based on CHC solving constraint Hom clause satisfiability problem is widely used. And this use of CHC is justified by the fact that the CHC satisfaction problem is as hard as the verification problem. So linear temporal property verification is also well studied. It is known to be pi 11 complete. And some approach, for example, the reduction to so-called the fair termination problem is widely used. And the use of fair termination problem is justified by the fact that it is as difficult as the verification problem. However, for branching time property verification, the complexity analysis and the canonical logical problem has not been known. And the aim of the paper is to give a comparison of logical approaches proposed for the problem, for the branching time verification problem, and propose or find the canonical or the best logical problem that is applicable for this verification problem. Okay. And this is a summary of the result. Perhaps interestingly, the hardness of the proposed logical problems are linearly ordered. Of course, the verification problem is easiest because it is reducible to any or other logical problems. And fixed point based approaches are relatively easier. And then extension of CHC is strictly harder than fixed point based approaches, and second order arithmetic is more far harder than these approaches. And sorry. Okay. And we also study the hierarchy inside this problem. So because this is higher order logic, there's a hierarchy given by the order of types used in the program or used in the logic. And we show that increasing the order of formulas makes the problem structurally harder. And I think that this observation is very interesting because it seemingly contradicts to the observation given by Kobayashi. So Kobayashi has shown that in some sense, verification problem and the validity problem of higher order logic are equivalent. But we prove that it is not the case in the presence of natural numbers as atomic type. So his observation, Kobayashi's observation, is for programs with only Boolean types. And our result is the programs with integers. And this difference of atomic types makes the situation very different. So I think this is very interesting. This can be an interesting observation. Okay, so this is a summary of the talk. Thanks.
Great talk, fantastic. So before I pass to the question of Slack, is there anyone that wants to ask a question to Takeshi? Okay, so Takeshi, there was a question in Slack by Noreen Conan, and the question is that if you think there is a suitable generalization of CHC that is as hard as the branching time property verification problem. So this is the first question.
Yeah, so it is very, I think it's a very interesting question. And I have no idea about its answer. So I tried to find such a problem, but as long as I tried, some extensions of CHC are strictly easier than the verification problem or strictly harder. So so I tried any, or perhaps all combination of usual well-known logical problems, logical connectives, such as conjunction, disjunction, universal and existential quantifiers, and no combination gives the exact characterization of the verification problem. So I think it may be the case that there exists somewhat unnatural logical connective, which makes the problem as hard as the verification problem, but I have currently no idea about such a connective.
Okay, and well, we have time for a last quick question about, I mean, the other question is about linear temporal property verification. So can you tell a little bit about this as well?
Yeah, so the second question asks whether the CHC with well-founded predicate can serve as a canonical logical basis for linear time temporal verification. And I think the answer is possibly yes. It is at least as hard as the verification problem, so it can serve as a canonical logical problem.
Thank you very much. So I would like to close the session now, and thank you all for the attention and for all the good talks. I mean, fantastic, and hope to see you all in the EATCS session award that is going to start in a minute or so. So thank you very much. Bye.